we're going to be looking at the 2021 Cape Chemistry Unit 2 Paper 1. Right, I'm going to take my time through some of the calculations that aren't so obvious, right, and then we'll just continue down the line with 2020, 2019, etc. Right, so if the question repeat right down the line, then I'm just going to be putting back the answer. If you need to look at how it is done, come back to this video to have a look. Right, number one, the equation for the formation of the anesthetic above. Right, an issue with this paper is that it's really hard to see sometimes, right, but we don't really need to care about the anesthetic per se. Right, in the reaction that we have here, we have bromine, right, in the presence of UV light. Well, the U and the V are really two different. UV light, right, and we know that that will create two bromine radicals, and this is free radical substitution. Right, we know it's free radical substitution. The hydrocarbon contains 87.8% carbon and 12.2% hydrogen by mass. Right, its empirical formula is, so in order to find the empirical formula from things like these, right, in order to find the empirical formula from things like these, I would suggest that we do it this way using the Jamboard. Hope you guys can see the Jamboard. Let me check. All right, you guys should be able to see it. Right, we're using 87 point what is it again? 87.8% carbon, and we say we have 12.2. I have to look back. It have to be 12.2, right? Yeah, 12.2% of hydrogen. And what we're showing here now is that we can just get these percentages as the mass, because if we have a compound, it has to be 100% of the compound. If 87.8% of the compound is carbon, then that must be the mass of carbon, right? And if 12.2% is hydrogen, that must be the mass of hydrogen. So we can translate it directly over into the mass per se in grams. Sorry, this should be 12.2 grams. Right, so we know what we do here now. We have to find the moles. Right, so we say 87.8 grams of carbon. We know moles is mass over molar mass. Molar mass of carbon is 12. Right, that is for carbon here. And then over here we have hydrogen, which is 12.2 sorry, grams divided by 1. Alright, so let me get my calculator. 87.8 divided by 12. Our answer here is going to be 7.3 thereabout. Let me check again. 7.3. Alright, thereabout. Alright, and then let's say 73.317. Alright, and then for this now it's going to give us 12.2 grams. And this is per mole. Wait, it can't be per mole. No. Moles equal mass. This is moles, right? So this is moles. Sorry about that. Right? Moles there. So I was saying about the moles here now. If I have 7.317, right, moles of carbon, and for hydrogen I have 12.2. Let me check back. 12.2. Alright, we're going to always divide by the smallest number. 7.317 divided by 7.317, because isn't this how we find the empirical formula? Right, we would have one carbon there. We have 12.2 divided by 7.317. What we're going to get? We're going to get 1.6 that we can round up to 2. So here we have 1 carbon and 2 hydrogen. Alright, hope that wasn't too long. And there we have B as the best answer. Hydrocarbon Z has a relative molecular mass of 84 when 0.1 grams of Z was burnt in oxygen. Right, 0.3 0.16 grams of carbon dioxide and 0.128 grams of water was formed. Now that seems like a mouthful, right? But we have to look at it like this now. We say we have Z, right? And we burn Z with oxygen. We don't know how much oxygen is there, right? I'm going to be mixing the crew. Oh, that's not a problem, right? And we're going to get carbon dioxide, we say, and we're going to get water. We don't know how many moles of carbon dioxide, we don't know how many moles of water, right? Let's call this, I don't know, should everything be X? I don't want to call everything X, you know, right? Let's say that we don't know, right? Let's call it Y and let's call this Z. Can't call that Z either. Let's call this A and let's call this B. Alright, call it A and we'll call it B, right? Okay, so we have to look at this now. We're saying that we have 0.1 mass of Z, right? Doing everything under each other of Z, right? That's a mass, right? And we say we have 0.316 grams of carbon dioxide, and we say we have 0.128 grams of water, right? Now we're probably going to have to find a more ratio to find out, right, how much oxygen is here and hence what its Z is. So in order to do this now, we're going to find number of moles. So we're going to divide this. Remember the molar mass, the molecular mass that we found, that was in the question, was 84. So we're going to divide mass by molar mass. This would be 44 for carbon dioxide because carbon and, yeah, 44, check it out, right? And water would be 18. Or what we're going to get now is 0.00112, 0.00172, wait, sorry, 0.0072, right? 0.0072. What you're going to get actually is some exponential value. But if you just write it regularly instead of in scientific notation, I think that is a nicer way to look at it when math bothers you. So I think that's a nicer way to look at it. And this will give us 0.0071. Remember what we do for empirical formula, right? We divide by the smallest, right? So we're going to divide by 0.00112, divide by 0.00112, divide by 0.00112, right? What we're going to get here is 1. What we're going to get here is 6.2. No, wait, not 6.2. 0.0072 divided by 0.00112. That should give us 6.4. My bad. Right? I'll work this out a little bit. So let me just 7.1. Check over them value there because 6.2 never look like it ever work. 0.00112. That should give us, makes sense, 6.3. And we can just round them off 6 and round this off 6. So we're saying that, right? Just watch it now, you know. We're saying that we have 6 moles of carbon dioxide, 6 moles of water, and 1 mole of Z. So let's fix up this equation now, right? We say we have Z plus, don't know how many oxygen, right? And it gives us 6 moles of carbon dioxide plus 6 moles of water. Alright, so we have that there. So in order for this to be balanced, right, oxygen, in order for this to be balanced now, we have 6 carbons and 2 6s, right, 6 carbons, right, and 2 6s, 12 hydrogen. So we don't know, say Z is C6H12, right? Oxygen would have be balanced out to be 9. So X is going to be equal to 9. This is 9 oxygen. So we know that it is C6H12. Hope that made sense. sense C6H12. Another thing that you could figure out now is that because the molecular mass is 84, that corresponds with C6H12. Never had to work out a thing, because they tell you that the relative molecular mass is 84. What is the molecular formula? You can just work out all of these to find the molecular mass, I mean. Right? And C6H12 should give you that. So you never even have to go through all of that. 4. Which of the following statement is true of the nitration of benzene? It's a reaction, it's an electrophilic addition reaction, because we know that the nitronium component attaches to the benzene ring, right? We can't, some people may be tempted to go to D, but this is dilute nitric acid, dilute sulfuric acid, it needs to be concentrated. Alright, so let's look at this now. So ethanoic acid, phenol, and ethanol. So item 5 refers to the following table, which shows the pKa values of 3 organic compounds. For which of the following properties are the compounds ranked in the correct order? So we have to watch this now, right? So we know that pKa, alright, so I think I'll just go back here. So I have to know that pKa, right, is inversely proportional to acidity. So inversely proportional to acidity. So working off of that first. So we know that ethanoic acid is the strongest, then phenol, then ethanol. We should remember. Ease of losing a proton, right? Protons acids are proton donors. That means that the stronger acid must have the easier, the higher the ease of losing a proton. Here it shows that ethanoic acid is higher than phenol, and phenol is higher than ethanol. So we're going with that. Stability now. We know that the stability of the of the conjugate base, right, isn't that directly proportional to acidity as well? Acidity or acid strength. Well, I don't want to do that. If I do that, I'm going to make it seem like I'm dividing. Or acid strength. Right? Acidity or acid strength. Same thing, right? So isn't the stability of the conjugate base proportional to the acid strength? The more stable the conjugate base, the easier the ease of losing a proton, because it knows it's going to be stable in that state as a conjugate base. So this means that F oxide ion will be the least stable, it will be the most unstable. And by the greater than and less than arrows or signs, this is true. Dissociation now. Ethanol has greater dissociation than phenol, and phenol has greater dissociation than ethanoic acid. That is not true. Because remember, when we talk about acid strength, right? The stronger the acid, right? The more the equilibrium of the reaction. Let's look at this HX. Give us H plus ions plus X minus, right? The more it leans to the, right? The equilibrium leans to the right. That means that the weaker acid would want to, that means that the weaker acid, right? So the strong acid, not the strong acid, yeah, the strong acid, yeah. Strong acid, right? We want to dissociate, but the weak acid would like to stay regular, because we know that its conjugate is unstable. So this means that ethanol will not want to dissociate more than phenol, and phenol will not want to dissociate more than ethanoic acid. So 3 has to be out is the best answer. Right? Here now, which of the following is likely to be the predominant first step in the reaction mechanisms for the reaction above? So here we see we have, okay, a halogen alkane reacting with sodium hydroxide. So this, I think it would be bromine we're talking about here. Let us see what's happening. CH2CH3, CH2CH3 bonded to the carbon right there, right? CH2CH3, I believe. kind of hard to read. And here we have CH3. Alright, and we have the bromine. Remember now, with tertiary halogenalkenes, it goes through what? SN1. Right? Is it SN1 or SN2? I have to remember, is it SN1 or SN2? So we say that tertiary halogenalkenes, right? Because we know that it's tertiary. So halogen is attached to the carbon, which is attached to 3 other R groups, right? So the tertiary halogenalkenes, right? They go through SN1, right? So we have to understand that type of reaction. So if we can look at the SN1 type of reaction, right, the unimolecular reaction, we have to know that there will be an increased slightly negative charge and a slightly positive charge here, causing the bromine to drag electrons closer to itself because it's more electronegative, right? This will be slow, right? It will be really slow, and what it will produce, right, will be an ion. So it'll be really slow, and it's going to produce a carbocation intermediate, right? CH2CH3, CH2CH3, CH2, I think, right? So we'll create a carbocation intermediate plus the bromine ion, the bromide ion, right? So I don't want the plus to be there, it looks weird, plus the bromide ion, right? And then we're going to have the entire reaction. We're looking for which one is the most probable first step, and it looks like A may be the most probable first step, right? Pentane has how many molecular form? Well, pentane has a molecular formula of C5H12, right? How many possible isomers does it have? Alright, so we're looking at this now. How many possible isomers does pentane have? So we know that N-pentane will just be C5. Alright, I'm not going to draw the hydrogen, just showing you C5, right? We're going to have a pentane that looks like this, which is going to be methylpentane. It will have to be 2-methylpentane, because if you put it here, you will just create a bent chain. If you put it here, just bent chain. So it has to be here or here. So it has to be 2 either way you take it, alright? And then we have one that can probably looks like this, right? And this would probably be dimethyl. So 2,2, right? 2,2 dimethyl propane. Sorry, this is butane, right? Sorry, butane here. So we're seeing this now, that this will probably be one, right? As well, if you do this, it can't work because it's just going to create a bent structure, right? So we have that there. So overall, we have 3 different isomers of pentane, right? Methylbenzene can react to produce that, right? Remember, in order to produce this, produce a halogen on the methylbenzene on the toluene ring, right? We're going to need a Friedel-Crafts catalyst with chlorine. So we have that there. Nylon 66 can be made by the condensation, polymerization of that and that, right? What will be the repeating unit, right? Remember, we're going to have a diol, right? A diamine, right? I think is that it's called, right? So the overall, what we're supposed to have is a constituent which has an OH, well, COOH, and a, I think, let me have a look at this, right? And it should have an NH over here, right? But remember, what's going to happen is that type of esterification type of reaction happening, right? So what's going to happen is that this will be broken off when it's reacting, and this will be broken off when it's reacting. So the overall thing you're going to see now, let me erase this. The overall thing you're going to see now, right, is the long lines coming from the nitrogen and the carbon. Remember, this is the nitrogen, right, and the carbon, and we're going to have this as a repeating unit, right? I just put R in there because that don't really matter. So what we're going to have here is R, right? The R, the air, the variable chain, right? CO going off, and we're going to have NH going off, right? So let's see where we have that. We have NH going off, CO going off. All right. Here we see UV light and chlorine again, electrophilic substitution. Tyrosine here now. The pH is most likely to be around 5.6. We have a basic area here, but we have two more acidic areas, right? More than basic area, so it will be slightly more acidic than basic, right? An alcohol is treated with potassium dichromate, and the resulting mixture gives a positive triiode test, which of the following structures best represents the alcohol. So remember, we're going to react with a secondary or a primary alcohol for the most part. Secondary or primary alcohol for the most part, right? So we're looking for this, right? Most likely it would be a secondary alcohol, so this would be out, right? Looking for this now, right? I think this would be out as well. Alright, so let's look at this now. A secondary alcohol, right? Most likely this is a primary, so most likely a secondary alcohol it reacts with. Alright, so we have that there. Let me see if there's anything else to this. Alright, and iodoform tests have to react on a methyl group. Phenol and benzoic acid can be distinguished by reaction using sodium carbonate. Remember that benzoic acid, organic oic acids, are able to evolve carbon dioxide from carbonates, but phenol is too weak. Therefore, if you mix both, if we have two different samples and we pour them on sodium carbonate, the one that evolves carbon dioxide is benzoic acid, and the one that doesn't is phenol. Here, we're looking at this reaction here. We're looking at, I think this is a CH3CH2 double bond CH, right? And we're reacting with hot acidified potassium permanganate. We know that we're going to create carbon dioxide and water. And if we create carbon dioxide and water, we're going to lose a carbon from the central chain, and we're going to get not 3, which is prop, but 2, which is eth, so ethanoic acid. Right, remember, if you have an issue with any of my answers, you can go into the comment section and let me know, and give me a valid reason as why it needs to be changed. Which of the following equation is correct for the reaction of 4-methylphenol and ethanol chloride? So we know that we're going to have the ethanol chloride combining not to the methyl group, right? And it's going to bind to the hydroxyl group, and it's going to produce hydrochloric acid. So I think that D is the one that fits all the criteria here. 16, which of the following statements regarding the components X and Y is correct? Alright, so we're saying that X more strongly is absorbed by the paper. That is not true. X is the furthest along, so it should be the least. X is more, well, here it says that, let me continue at A. Absorbed by the paper, and X is a larger RF value. X does have a larger RF value than Y. Remember, RF value measure the distance from the starting point, right, and then end point. So here we have a inaccuracy at the first statement and true last statement. X now is more strongly absorbed. Inaccuracy. and y and x as a smaller, that wouldn't make any sense in accuracy there. Y is more strongly absorbed, I would believe that. And y at a larger, if y is more strongly absorbed, it won't have the larger R value. That is inaccurate. So y is more strongly absorbed, yes, and y has a smaller R value, yes, D. Right, what would be observed when aqueous bromine is added to the following compound? So we already have this. Remember that the hydroxyl group is orthopara projecting, so I don't think bromine will attach anywhere else, and you didn't even say you're adding a Friedel-Crafts reagent or anything like that to make it stronger. So I do believe that we will have no visible reaction here, as I don't believe that bromine will be strong enough to break the relationship here. A compound absorbs light at frequency 940 megahertz. The wavelength in centimeter of the light absorbed is, right? What would it be? So we have to look at this now. So if we remember wavelength lambda, right? Let me change back to black. Right, wavelength lambda should be equal to the speed of light over the frequency. The speed of light is 3.0 times 10 to the 8 meters per second. All right, and then we have the I was going to say volume, the frequency V. Now the frequency is 940 megahertz. 940 megahertz. And remember, we need to convert this to hertz, right? Mega, remember the prefix mega means 1000. Therefore, in order to convert it to hertz, we must have 940 times 1 times 10 to the 6th power, or 1 million. So we're going to have 940, 1, 2, 3, 4, 5, 6 divided by that. Alright, so what are we going to get? Let me do it real quick. 3.0 times 10, right, to the power of 8. Right, divided by 940, 1, 2, 3, 4, 5, 6. That should give us 0.319, right? And this will be meters, right? In the question it says it wants it in centimeters, right? So if it is in meters, even if you use a simple kick him down Mary, don't commit murder, right? We're at meters, decimeters, centimeters, right? So we just go back 1, 2. What we're supposed to get is 31.9. The answer is 31.91. Right? The calculator actually has 1 after, so I think I should really put the 1 there. Okay. Treatment now of 10 gram sample. A 10 gram sample containing a chloride salt, we don't know which salt it is, with excess silver nitrate solution provides 8.08 grams of silver chloride. Right, so which of the following expressions could we use to calculate the percentage of chloride salt in sample? Now this percentage now is going to be a little bit tricky, well, a little bit different. So we're saying that we react to create silver chloride, and we have to know, calculate the expressions, calculate the percentage of the chloride in the sample. Right, so we have a 8.08 grams of silver chloride, right? And we have to know how much is in the sample. So I think we're supposed to look at the reaction that we have. Silver ion plus the chloride ion gives us, right, silver chloride. We have to understand that they are in 1-to-1 ratios. Simple thing, if you remember the KSP, right? Simple dissociation reaction or combination reaction as I have here, right? Now we need to determine, right, the moles of silver chloride, right? the amount of moles of silver chloride. Because if we determine the amount of moles of silver chloride, then it would be 1-to-1 ratio with chloride. Right? We don't have any information for chloride, but we have silver chloride. We know that silver chloride is 8.08 grams. And we must divide it by the molecular mass of silver chloride. Silver chloride's molecular mass is around 145.5. Right? Let me check it out. Alright, 1.145.5, I mean, right? So we need to take that. Alright, so we have that so far. Right? In order to find this would be the number of moles of chloride ions. Right? In order to find the number of moles of chloride ions remaining in the sample, right? Overall, we need to times it by the the atomic mass of, right, the atomic mass of chlorine, right, and divide it by the overall sample, right? And if we need now to get the percentage, all we do now is times everything here by 100. So we need to find something that looks similar to this. So it's 8.08, right, over 143.5, right, and 35.5 over 10 times 100b. Right. Now, a student carries out the gravimetric analysis of a solid sample taken from... What is all of this, man? A solid sample is found to be contaminated with lead ions. 100 centimeter cube of a solution from a sample, when mixed with 25 centimeter cube of 0.1 mole DMQ, HCl yields 0.010 grams of lead chloride, and we get the relative atomic mass. All we want to do now is balance the equation. Notice how the whole of this useless. All of this useless. Alright? Except for a little piece of it. Looking at the yield of lead chloride. Right? So we're looking at the entire balance equation. We know that lead ions will be used. Therefore, A and B. A and B not saying anything. Alright? Anything useful, but looking at the yield, we have 0.010 grams of lead chloride yield, so we can see that that is sparingly soluble, right? Wonderful. Which are the following sets of regions in the electromagnetic spectrum is correct in increasing wavelength? So we see that we're going to have X-rays, then UV light, then visible light, then IR. Right? Now, the transitions expected in that molecule in a UV-VIS spectrum. Now, we know that if you have UV-VIS activity, you need to have free electrons, right? Lone pairs. And you need to probably have a double bond or so. Now, what I can tell by this now, I don't know how much carbon here because I can't read that. And I think it's 7 hydrogen. But I don't think that matters because that is the non-polar section of the components, the alkyl group. Looking at the sodium, the nitrogen here, oxide, we're going to see that there is lone pairs and a double bond. So it must can be present within, it must be active within the UV-VIS spectrum. And the UV-VIS spectrum will have N to pi, well, pi to pi star, N to pi star, and N to sigma star. Alright, we have that there. An unknown organic compound with a molecular mass of 48 grams. 48 grams is carbon dioxide. But let's continue reading. Analyze using infrared. Yes, it's carbon dioxide. 48 grams. Alright, here now. Let's have a look at this. Item 24 refers to the following information. A student used gravimetric analysis to determine the percentage by mass of calcium in chalk. The student weighed 2 grams of chalk and dissolved it in HCl, then added excess ammonium oxalate to precipitate the calcium ions. Right? The precipitate was filtered, dried, and weighed. The percentage by mass was then calculated. It was found that however the result obtained was lower than expected. Which of the following sources of error could possibly account for this difference? Now, if there's incomplete drying, we know that water is still left there. That means that that error would allow it to be higher than expected. So that would be out. Using wet sintered glass crucible will allow water to seep in, creating a hydrated compound. That means it will be higher than expected, not lower as seen in the question. Other ions precipitating out would allow it to be higher. So I think it's incomplete precipitation would be the only thing that would allow it to be lower. Infrared spectroscopy is widely used to monitor atmospheric pollutants, which of the following atmospheric pollutants is not usually monitored by infrared spec. I think it is oxygen there. The mixture containing heptane, 2,2-dimethylbutane, hexanoic acid, and heptanol was separated by gas-liquid chromatography. The stationary phase used was polar. Which are in what order would the components leave the column? Right? So we're saying that it's polar. Alright, so the stationary phase used was polar. So we're going to look at which ones would leave the column. The ones that leave the column would be less attracted to the polar stationary phase, right? So they will move much faster than the other fractions or the other segments, right? The other, I don't even remember the term. The other things, the other liquids, right? Because we're looking at separation. Right, so they will move much faster. So we're looking at here which one is the most non-polar to not react with the stationary phase, which is polar, to leave the column first. We're looking at the most non-polar one. So with that, we say heptane may come out first, yes, but heptanol can't come before 2,2-dimethylbutane. Ethanoic acid would definitely come last. Heptanol would definitely come penultimate. Right, so we have to find the two most non-polar things will come out first, then the two most polar things will come out last. Mixture of the nitric acid here and water shows a positive deviation from Raoult's law. See that the curve upwards, right? Let's look at this. In the chromatographic experiment here, within it, the mobile phase was tetrachloromethane. So remember, the mobile phase is non-polar. That means that the mobile phase is non-polar. That means that the mobile phase is polar. So the component A is most soluble in the stationary phase. Yes, so most soluble in the stationary phase. So we're looking at this. Alright, true, because most soluble in stationary phase. Let's have a look at that. Component B is more polar than component C. Yeah, I believe that these are two ones. But C cannot be more polar than all of them, because C would have been where A probably is. So 1 and 2. 29. Which of the following bonds would show the strongest absorption in IR spectroscopic analysis? Right? So remember that, right? IR activity is directly proportional to bond polarity. If nobody ever tell you that, remember say me tell you that. So the ones that is most polar would be the ones that have the most difference in electronegativities, which I would believe would be oxygen and hydrogen here. Right? 30. During a chemical reaction, disproportionate, this is unit 1 content, man. Disproportionation happens when one section or one substance, right? One substance is both oxidized and reduced, meaning that it will be both the oxidizing agent and the reducing agent. Which of the following is not a greenhouse gas? Ammonia. Right? Can't really teach that. Right? Which gravitational mode for carbon dioxide is not expected to contribute to greenhouse gas? Right? So we have to look at this. Right? We know that this is symmetric. asymmetric. This is this is some amount of twisting or bending as well, and this is bending. Note now, right, what would contribute to this? We have to look at the absorption, right? Now the absorption, when you twist and bend and vibrate, you have to have a change in dipole moments. Note now, with symmetric now, we're going to have both things increasing, right, relatively at the same rate, allowing for the, well, let's call this that, allowing for the charges to remain vaguely the same. So it would be vaguely in the same area as usual. So showing that, right? Which was the next one? Asymmetric. Asymmetry now it will be a difference. So I'm just showing this. There will be a difference. That these would be less, right? And this would be greater. So it'd be a greater change in the polarity, right? If we were to bend it now, right? They were supposed to bend it now. And this is more negative and this is more negative, right? Well, more negative. We're going to see a more positive area here. We're going to have a complete dipole going through, so where most of this area is negative and most of this area is positive. So you're gonna have change in moments. So the only thing that doesn't really have the full change here, well, that would be incorrect there. Let me draw the arrow properly. The only thing that won't have the full change here would be symmetric, right? So symmetric won't show so much of the activity here, all right? So A would be the best answer. Right here now, the two equations below summarizes the fermentation process for the production of alcohol, right? So we know that we have water and sucrose, right? So sucrose is here, C12H22O11, and then we're supposed to have zymase and that byproduct to create the ethanol and 2 moles of carbon dioxide. Right, which of the following products is not not produced, for commercial purposes by the electrolysis of brine? This would be oxygen. What is the product of the following unbalanced equation? This would be AlOH3, and this should be solid, right? We should remember this unit 1 content, right? If you did unit 1 before. Which of the following is a major component of biomass? Cellulose. 37. Which of the following, because cellulose is one of the most abundant substances on earth, unit 1 biology, right? 37. Which of the following elements has the highest electronegativity? Unit 1 chemistry. Sulfur will be the closest to fluorine, which has the highest electronegativity. As we go across the periods and up the groups, we're going to have increase in electronegativity. Across the periods from left to right, by the way. 38. Which of the following methods are used in water purification? Right, we have distillation, filtration, right? Distillation to remove any other dissolved liquid components, filtration to remove any type of solid components, right? And UV to kill any type of microbial components, right? Or microbial, life. D. 39. In the production of sulfuric acid by the contact process, the following exothermic reaction takes place, right? Which of the following conditions would favor the forward reaction? So looking at the forward reaction here. So we're going to have to lower the temperature, right? And we're going to have to do it in excess oxygen, right? Because if we lower the pressure, right? Let's see what's happening here. Let me see the Chatelier's principle. This is unit 1 as well. The Chatelier's principle, what the Chatelier's principle states, right? Isn't this an exothermic reaction? If this is an exothermic reaction happening under high pressure, right? Or if we lower the pressure, we don't want to do that. Alright, so 2 and 3 only. Because we have low temperature, it's going to, if a reaction is exothermic, we must cool it down. right? In order to keep reaction going, and we have to have excess oxygen for the contact process to generally work. 40. A sample of crude oil contains mainly that. I believe the answer here is kerosene, right? More so than diesel, but some people would choose diesel. So if you have an issue with this, please tell me what you think would be the best answer for this, right? In which layer of the atmosphere does ozone act as a pollutant? This would be the troposphere. Wonderful. And here we're looking at primary and secondary pollutants. Primary pollutants are one being directly from anthropogenic impact, right, human impact, and secondary are being made up of primary, right? So hydrocarbons, so aldehydes and ozone are secondary. Let me see, aldehydes and ozone, they would be secondary, right? Let's just focus on this first. Nitrogen oxide would be primary. We're seeing as nitrogen oxide produced, right? It's primary there. And we know why it's primary, because we see the increase in aldehydes and ozone as nitrogen oxide is produced, right? So we see that aldehydes and ozone are reliant on nitrogen dioxide and nitrogen monoxide to be produced. Therefore, these are true. But hydrocarbons are released from crude oil processes. They are usually primary, so they can't be secondary. So 1 and 3 only. And that is the full explanation of the chemistry unit 2 2021 paper 1 paper. Right, I'm going to be moving to 2020 now and 2019. So if I skip over something and don't give an explanation, please come back here to check it out. If this was helpful, please leave a like, subscribe, and share the video so other persons can benefit. All right, so thanks for watching.